All right, Jacob, what's your question now?
So for that theorem 2.6.1, I was wondering why you get the full integration factor when you only get it in respect to x or y. Like why you can only why if you do one or the other, it works just with one
Oh, okay.
and
Um,
not both, if possible.
yeah. So this is actually a really this is a really weird question. The answer to this question is a little weird. Um, how about if I phrase things firstly, just reminding about the general concept of an. Have you guys watched the integrating factors videos yet? Okay. So here's the gist of it, the idea of an integrating factor. Suppose you had an equation that looked like mdx plus ndy is, say, 0. Are these forms that have been happening?
Mm-hmm.
Okay, so when they're phrased this way, what's the first thing you do? What do you do? What have you guys have been doing this for a couple of days now, probably, or for at least 3 or 4 minutes as you've been frantically finishing your homework for tonight.
Like what I do to solve?
Yeah, like if you're presented with one of these, what's your first step?
Take the partial derivatives of
Yeah, you're running the test for exactness, right?
yeah.
Okay, so we test for exact. We get, let's see. So I'm going to take my, and either my is equal to mnx or my isn't. You guys with me on that? In the left case, okay, yeah, it's equal, it's exact, check. Then, like, f is either the integral of m dx or it's equal to the integral of n dy. And in fact, it has to be both. So you go find this friggin' thing, right? You guys can do that technique. You've been running this for a couple of days. So this isn't so bad. You like go find f, get f of x and y equals a constant, circle this, move on with life, right? Okay, so the idea of an integrating factor is, all right, in the case that it's not exact, then what do you do? Well, there's something really horrible that somebody noticed a long time ago. They noticed that it's possible that you could multiply this function through by something, have it become exact, and then you could solve that equation. You guys with me on that? So, like, you could say, oh, if I just multiply this whole equation through by some function mu, I get this new equation, right? It's got like a new m and a new n, and it's still equal to 0. You guys see this?
Can we use something other than mu?
Sure. What do you want to use?
Anything. It looks too much like an N.
Oh, that's totally fair.
You need to make your other end more long.
Let's call it I. Right? You just pick this function out of the air and slap it on there, and then you get a different differential equation, right?
Mm-hmm.
So what do you do when you have this differential equation? Well, you do the same shit you just did. Test for exactness. If it's exact, then you solve it. If it's not exact, then you're kind of shit out of luck, but you can multiply through by a different function. You guys see, like, this is the dumbest method that you could kind of conceive of. It really could just continue. Like, you could just try multiplying by all the functions you know until you happen across one that works. It's real dumb. It's a terrible idea. The really jack thing, it works. And sometimes it's a good idea because sometimes it's the only fucking way to solve things. It's terrible. The analogy that I use in a computer science class would be that this is a lot like sorting a deck of cards. Like you want to sort your deck of cards out to see that they're all there. So one way you could sort a deck of cards out is you could shuffle it and then check if they're sorted. It's real dumb, but shit if it doesn't work. Like, it's not going to work for a deck of cards because you're going to freaking shuffle your thumbs off doing it. But a computer can actually sort stuff this way. It's a terrible method. It's simultaneously the worst available method and also one of the best ones. It's the worst available method because it takes forever, right? Like, it may never stop. It's also the best available method in that it might work on the first try. So there's this horrible gambler's fallacy of like, but it might be really, really fast. Right? So this is the idea of an integrating factor is if you multiply through by some function and then make your equation exact, the thing that you multiplied through by is an integrating factor. So this function I, so if we have a not exact equation here, and then we get an exact equation here, then this function I is called an integrating factor. It's not named very creatively. It's just a factor that you multiply through by, and then you can integrate, right? Like, so there's this theorem in the book that says essentially, if you have this fact, right? So if you've got your differential equation. So here's my differential equation, right? So I've got my differential equation. If I've got some continuous partials, and if my minus nx over n is independent of y on r, and then we define this p, then this kind of funny mu created this way is actually an integrating factor. Now, why is this the case is a little bit tough, but it turns out that, let's see, essentially it turns out to be the product rule that makes this work. So let me drill on your question here, Jacob. Is your question why is this a valid technique, or is your question kind of how is this executed?
Not really why it's valid, but my main question was like, if both ways work, why is it only one of them that you can use? Like, if you get mu's for both of them, but they're different, and they're both of single variables, why, if you go back and multiply by that integration factor, you only use one of them?
Oh, why is only one of them necessary?
Yeah, because in the book it says mu can be a function of x and y.
It certainly can be.
Yeah.
And this is the shuffling problem. So this is not saying that these are the only ways to get integrating factors. It is saying that if these things are the case, then there is an integrating factor and it looks like. Because generally speaking here, an integrating factor can look like anything.
Mm-hmm.
And so if you don't have any guidance on when an integrating factor exists and what it looks like, you can literally just try anything.
Okay.
So you might see let me go grab an example to play with here.
I think I see it now, because I just realized it's because you set for instance, for A, you would set Q of Y equal to 0, and that's why you would, or define it as 0, and then solve for P.
Oh, I see. Yeah, and then it should be noted, right, that you have to be just a little bit careful, because if you multiply through by something that's pretty often 0, you can wipe out stuff.
Mhm.
You guys see that? So this integrating factor that you're multiplying by, for instance, the integrating factor 0 is probably not super useful. Right? It does make an equation that's true, but it's not really solved. Does that make sense?
Will it always make it true? Or is there any case in which it's not true?
Well, if you multiply both sides of an equation by 0, you're going to get 0 equals.
Okay, I just want to make sure because I was looking at that and I was like, yeah, that seems like a cheap thing.
Yeah, it's really just that the solution, right, should look something like, f of x and y equals a constant, right? You should have some relationship between y and x. Whereas if you have if your equation turns into 0 equals 0, that doesn't give you a relationship between y and x, right? You've kind of overdone things, and now now it's not that there's a solution, it's that everything's a solution. So it's possible that you might accidentally introduce some solutions by multiplying by certain integrating factors.
Mm-hmm.
Does that make sense?
Yeah.
So really what you should do is you solve this, you get some function, and then you should just double check quick that function is actually a solution to the differential equation you started with and not an artifact of your integrating factor. So let's try a very quick and easy example. Let's see. So I think I assigned you odds.
No, I think it was all of them.
Oh, it was all of them? Good.
No.
All right. Well, I'm gonna do one of your homework problems for you then. All right. So let's see if we can puzzle through problem 4 here. So first things first. What's m? What's n? And do I have the assumptions of theorem 2.6.1 satisfied?
Well, m is the part before dx.
Okay, so that's m.
That's n.
This one's n then?
Yep.
Okay, so I need to verify that mn, my, and nx are continuous on some open rectangle. Are these continuous on an open rectangle?
They're polynomials.
Solid. They're polynomials in x and y. They are not only continuous on an open rectangle, they are continuous on any open rectangle, which is a lot better.
Yeah.
Okay, so I feel like I can write check on continuity. Right? So now I'm thinking, all right, so in the case of my function here, I'm going to calculate the top part of these two fractions, and I'm always going to do that. So this one's my minus nx, this one's nx minus my. So I'm going to just calculate my minus nx.
By the way, I did not realize that for so many problems. And
yeah, and if you do them backwards, they don't really work.
No, I kept getting 1 over y squared instead of just y squared, and I was like, what am I doing wrong?
Yep.
Yeah.
Yeah, this is an important realization, is that these two things are flip-flopped from one another. So you can always calculate my minus nx, but when you're looking at part B here, you need to flip this sign on it to use it. So my is 3x squared. What's nx?
6x squared.
Okay, so I'm subtracting 6x squared. And so I'm out of that, I got minus 3x squared. Okay, now to kind of consider part A here, right? I need to calculate my minus nx over n. And so in my case, that's going to be minus 3x squared over, well, n was 2x cubed. And all I need here is that this doesn't have any y's in it. You guys with me on that? This is purely a function of x. So we are independent of y on a rectangle. Cool. Then my integrating factor is plus or minus e raised to the integral of that thing. Everybody with me on that?
Mhm.
So do I need to check part B?
No.
No. And don't. If this had failed, right, if this thing had y's in it, then I'd be checking part B. If part B had x's in it, right, in other words, if both pieces failed, then I'd probably think to myself, oh shit, maybe finding an integrating factor isn't real easy for this one. Really, in the problem set, I'd think to myself, oh crap, I took a derivative wrong. I better go back and look at that. Or I put the wrong thing on the bottom of the fraction. But in reality, yeah, integrating factors just aren't that easy to find. Okay, so simplifying this a little bit, since I'm going to have to integrate it, I got minus 3 over 2x. And so my integrating factor, mu, with a very long tail, so Jordan can tell it from the m's, is going to be plus or minus e to the integral of minus 3 over 2x dx.
By the way, I think your tail's on the wrong side, but I won't give you too much shit about that.
You know what? There you go. Now it's not even a mu. It's just some random bullshit squiggle. All right, fine. I'll make an effort with my handwriting.
There we go.
Okay. So I need to actually integrate this thing. So that's going to be plus or minus e to the integral, to the minus 3 halves times the integral of 1 over x dx. So I'm going to get plus or minus e raised to the minus 3 halves log absolute value of x. Pretty good with that?
Mm-hmm.
You really should have a plus c here. Doesn't really matter. I'm keeping track of this plus or minus 2. That also doesn't really matter. Gets with me on that? In the end here, I'm just going to end up by multiplying. I'm going to end up multiplying by the positive version. I don't really care whether you keep track of the plus or minus. Why doesn't it matter?
Is it just because you're making a different equation anyway, so it doesn't really matter?
Yeah, you're multiplying both sides of this equation through by this plus or minus, right?
Mm-hmm.
Well, the right-hand side's 0, and the left-hand side's just a sum. The only thing I really care about is the test for exactness, and the plus or minus isn't going to make any difference in that test. It's going to be exact either way. The only reason they put it in here is if you have two negative terms, you can make them both positive and just make your life just a teens easier. All right, so all told out of this, I'm going to get plus or minus the absolute value of x raised to the minus 3 halves power. Everybody good with that? Which I'm going to be lazy enough to write as x to the minus 3 halves power, even though I probably shouldn't. I guess I'm going to think this out. You guys all good with that? Okay, so now what am I going to do with this thing? Well, I'm going to multiply both sides of my equation through by this. So I'm going to take this equation, I'm going to multiply through by x to the minus 3 halves power. So that's going to give me Well, it's going to leave 3 alone. How about x squared times x to the minus 3 halves? What do you get? How many halves is 2?
4.
So I'm going to have x to the 1 half times y. And then I'm going to have plus 2, let's see, x cubed is x to the 6 halves. And then somebody took 3 of my halves away. So I'm going to have 2x to the 3 halves. You guys with me on that? And then, oops, I lost a dx here. Why'd you guys let me get rid of that? Then I'm going to have a dy and an equals 0. All good on this? Okay, and this is the trick here. It's like after I multiplied through by this integrating factor thing, now what?
Solve it like you would normally.
I'd probably check for exactness
Oh.
first, just because it'll be real frustrating if I don't check for exactness first. But technically, you don't have to. Like, since this satisfied since my mu was found using the theorem, I know that this is going to work. This is not a guess at an integrating factor. The theorem says this actually does work and is an integrating factor. So technically, you don't need to check for exactness here. What the hell? I'm going to do it quick. I need this is playing the part of m, right? So now I've got my new equation, right? So I've got like m hat dx plus n hat dy equals 0. And so I just need to check whether m hat y is equal to n hat x. So the y derivative of this thing is 3x to the 1 half, and the x derivative of that thing is 3x to the 1 half. Okay, cool. You guys all good on that?
Mm-hmm.
All right. So next thing next, what do I do? So now that I know for sure that this thing's exact, what's my next step?
Take the integral of the easiest one.
Yeah, you just need to integrate either this one dy or this one dx. These are both pretty chill, but it feels like the dy integral is going to be really easy. It's going to be slap a y on that shit. So I'm pretty sure I got f of x and y is going to be 2x to the 3 halves y plus a constant. Guys with me on that?
Mm-hmm.
Okay, what do I do with that?
Take the partial derivative with respect to x, which should equal m.
Yeah, just cool. So we took that part and integrated dy. We got this. Notice that if we partial with respect to x this thing, we get this guy exactly. So this basically checks out. And so that means that my solution is f of x and y is 2x to the 3 halves y. And so my answer is what?
C equals 2 to the 2 times x to the 3 halves y.
Okay.
Wait. Oh
Good
yeah, I was
catch.
gonna say. Like you
were gonna say, Joe, there should be a y in there? That's fair. There should be a y in there. All right, now what do I do with this thing?
You could solve for y.
Yeah, this one I really should check that it satisfies the original differential equation because, like, I'm a little worried. I multiplied through by something. What if I made this happen? Should be just a little bit concerned about that generally with integrating factors, especially in the case that you multiply through by something relatively complicated, right? Because if you accidentally multiply both sides of an equation by something that's like, I don't know, always zero, and then you claim that that thing is the solution, you might have a real problem on your hands. Like if I multiplied both sides of this thing by the quantity y minus x, and then the solution I got was y equals x, I'd be a little bit like, wait a second, I did that. So I just want to check that this thing solves my original differential equation. So how do I even do that? Does that question feel weird?
Are you talking about the one before the integrating factor?
Yeah, I'm talking about the original one, right? Remember, they asked me a question originally, and then I answered a different question, and now I'm wondering if that even worked. Like, is the question that I answered, does it have the same answer as the original question?
Well,
It feels like it should, right?
I don't know if this is how you would necessarily do it, but I would rearrange it. So it would be the 3x squared y plus 2x cubed dy over dx.
Oh, good thought. Yeah, take this friggin' thing. Right, so here I'm kind of doing my to verify. Okay, so I took my original differential equation, which doesn't really look like a differential equation. So I'm going to rearrange it to look like a differential equation. So I'm going to multiply through by 1 over dx. So I'm going to have 3x squared y plus 2x cubed y prime is 0. You guys see this is now a differential equation?
Mm-hmm.
Okay? I'm going to take this thing, and I'm going to check that this satisfies this guy. So the way I'm going to do that is I'm just going to take this thing, and I'm going to hit both sides with a ddx. If I use the product rule here, I'm going to get 2 times ddx of x to the 3 halves times y plus 2 times x to the 3 halves times dy dx, and that's going to equal 0. You guys with me? Okay, this stuff. You guys see how this doesn't really look like this one? Why are these different? First, are they different?
Oh, it's because you didn't multiply the other one through by your integrating factor.
Yeah, I haven't really multiplied through by an integrating factor here, right? Oops, that really was a 1. I don't know why I fixed that. Yeah, so I noticed that, all right, when I apply the product rule to this thing, I got 2x to the 1/2 times, oh, why did I do that? Sorry, let me do a little arithmetic in my head instead of being a goofball. So I got 3x to the 1/2 times y plus 2x to the 3 halves times y prime is 0. And I'm like, hey, wait. This thing feels similar to the differential equation I was asked about, but the difference is this thing that I multiplied through by, right? You see, like the powers of x are just off by a little bit. But if I'm kind of multiply both sides through by x to the 1/2, Whoops, that's not right. How about x to the 3 halves? I get these same equations. You guys see that?
Mm-hmm.
Okay, now, am I allowed to do that? That's the integrating factor again. Guys with me? So what the heck, man?
Since you do it to both sides, yeah.
Yeah, I mean, it's kind of a valid arithmetic operation, right?
Which is really annoying.
So you really should be worried about when that thing is 0, right?
Mm-hmm.
So when am I multiplying both sides of this equation by 0?
When x is 0.
Yeah, only when x is 0. Is that going to really affect a derivative? No, it's just a single point, right? Okay, so another way I might see this is if I could solve this thing explicitly, which in this case I actually can, right? So this is kind of in pink here. This was the like implicit idea. You guys see that? Another alternative would be if I could solve that thing, I could get y is c over 2x to the 3 halves, which I could maybe rewrite a little bit as some different constant x to the minus 3 halves. You guys with me on that? Okay, so how do I check whether this thing explicitly solves this differential equation? What do I do?
Take the derivative of it and then plug both in.
Good. So I'm going to get k times minus 3 halves x to the, let's see, one lower power from minus 3 halves is how many halves?
5 halves.
Minus 5 halves. Good. Okay, and then I should just take these and plug them in here, right? So I'm going to evaluate this at these guys. So I'm going to get 3x squared times a constant times x to the minus 3 halves plus 2x cubed times a constant times minus 3 halves x to the minus 5 halves. And I'm wondering, is this equal to 0? You guys with me on that? Okay. A little bit of canceling probably here. Let's see. So I got 2's that cancel. This whole thing is 3k. Let's see. That's an x to the 1 half. Right?
Mm-hmm.
Fractions are hard, yeah. You're like, damn it, if I'd known there's adding halves, I probably would have dropped this class a couple of weeks ago. All right, and then this guy, I've got a minus 3k, which seems hopeful. And then that's 6 halves, take away 5 is x to the 1 half. And I'm wondering, is this 0?
Not sure. All
Yep.
those fractions got my brain scrambled.
Yeah, notice that the fraction adding you're doing in here feels a lot like the multiplying through by the integrating factor here. Because it's all the same shit. Like, there's nothing new here. Right? Does this make this make a little more sense? Basically what's going on, right, is I'm kind of cheating the product rule out. And the integrating factor is just the right thing to cheat the product rule with. And the problem is it's really hard to find the right thing to cheat the product rule with, but it might be there, so you can keep looking forever if you wanted to. One of the real weird things is that and maybe I shouldn't. I'm pretty sure I'm right on this. I believe it is the case that if a differential equation like this has a solution, there is always an integrating factor. Let's see, is that correct? Yeah, I'm pretty sure that's correct. Which means that you know that there is one, and so you can always fiddle with it until you find one. The problem is that it might take long, like heat death of the universe kind of time to guess an appropriate integrating factor. But knowing there is one is really frustrating.
It'd probably take just as long to do that as it would to guess every integrating factor, as we were talking about before.
Yeah, that's exactly what I mean. It's like you could keep trying, right?
Yeah.
This is a little bit like, you guys ever dropped anything you really liked in a river? I dropped a pair of sunglasses in a pretty cold creek in Montana one time that was about ankle deep while I was fly fishing. It was the dumbest thing. Pair of black sunglasses, lots of, kind of ripply water. It's like this deep now. How long do you look for your pair of sunglasses that you really like in ankle deep water? I don't know, it depends. Same thing here. How long do you look for an integrating factor? Depends on how bad you need one.
Depends on how much points I'm getting for it.
Yeah, I mean, the nice thing about this theorem says, if it's one of these two cases, there is an integrating factor and it's given by this. The worst case of the world is there is always an integrating factor if you can write a differential equation like this. Good luck finding the bastard.
So you're saying if it's in the form m plus n, it has an integrating factor?
Yeah, I believe that to be true.
Okay.
So I believe that if you can write a differential equation as m dx plus n dy, and m and n are both sufficiently continuous, then there exists a solution, it's unique, and the way you can find it is with an integrating factor. The problem is that just because there is an integrating factor doesn't mean you can find it.
Jeez.
So, like, just because I know my sunglasses are in the creek doesn't mean I can lay my hands on them. Those sunglasses are still in the bottom of that creek.
It's quite a sad analogy.
Well, I guess they might not be, but they probably are. All right. Any other questions on the ideas of integrating factors? They're a little weird, right?
Yeah. I don't like the idea of multiplying both sides when one side is a 0.
Yeah, it feels like cheating. It's it's super weird that it works. What's real weird is that the solution to the new differential equation is actually the solution to the old one. You don't have to like multiply or divide by the integrating factor in any way.
I was gonna ask that.
Yeah, it feels real wrong. But it is really just if you look through our kind of implicit idea, it really is just that when you implicitly differentiate, if you multiply both sides of the derivative you get the equation. You guys see that?
Mm-hmm.
So like if I use the integrating factor to turn my equation into this other equation and then solve it, in order to see the solution, I just multiply back through by it. It's real weird. Feels like it shouldn't work. Still does for some reason.
That's just this entire class. First it was the variation of parameters, and now it's this.
Yeah, that's definitely the case here. There are a number of things that are real surprising in here, and feel like they shouldn't work that just do. Yeah, welcome to Applied Mathematics. It has a whole bunch of those things in it. All right, any questions on this?
Mm-mm.
Okay.